Welcome to this presentation. In this model, I'm gonna speak about microstrip antennas. Printed antennas are constructed using printed circuit fabrication techniques such that the portion of the metallization layer is responsible for radiation. Microstrip antenna patch elements and array of patches are the most common form of printed antennas and were conceived in the 1950s. Extensive investigation of patch antenna began in the 1970s and resulted in many useful design configurations. Printed antennas are popular with the antenna engineers for their low profile, for the ease with which they can be configured to specialized geometries, and because of their low cost when produced in large quantities. So now a microstrip device can be defined as in simplest form, a layered structure with two parallel conductors separated by a thin dielectric substrate and the lower conductor acting as a ground plane. If the upper metallization is a long narrow strip, a microstrip transmission line is formed. If the upper conductor is a patch that is an appreciable fraction of a wavelength in extent, the device becomes microstrip antenna as shown in this figure. So this diagram shows the field along the microstrip antenna, and this is the top view of the microstrip antenna showing the length and width of the strip. The resonant nature of microstrip antennas also means that at frequencies below UHF they become excessively large. They are typically used at frequencies from 1 to 100 GHz. Microstrip antenna have high radiation efficiency with the desired polarization, impedance and bandwidth. So figure shows the most commonly used microstrip antenna, a rectangular patch antenna being fed from a microstrip transmission line. The substrate thickness T is much less than a wavelength. The rectangular patch is usually operated near the resonance in order to obtain a real valued impedance. So an approximate value for the length of a resonant half wavelength patch is L is equal to 0.49 lambda D. That can be written as 0.49 into lambda by square root of epsilon r, where lambda is the free space wavelength, lambda D is the wavelength in the dielectric, and ER is the substrate dielectric constant. Okay. And the rectangular patch antenna being fed from the microstrip transmission line, the substrate thickness T is much less than a wavelength. A rectangular patch is usually operated near resonance in order to obtain a real valued input impedance. Models are available for determining the resonant frequency with the cavity model, usually yielding accurate results. The fringing fields act to extend the effective length of the patch, and thus the length of the half-wave patch is slightly less than the half wavelength in the dielectric substrate material. Okay, and this is similar to the foreshortening of a half-wave dipole to achieve resonance. The amount of length reduction depends on epsilon r, T, and W. And the region between the conductors acts as a half-wavelength transmission line cavity that is open circuited at its ends. So the electric fields associated with the standing wave mode in the dielectric, where the electric field lines are perpendicular to the conductors as required by the boundary conditions, and they look much like those in the parallel plate capacitor. So the fringing fields at the ends are exposed to the upper half space and are responsible for the radiation. The standing wave mode, the half wavelength separation between ends leads to electric fields that are of opposite phase on the left and right halves. Right, and therefore the total fringing fields at the edges are 180 degree out of phase and equal in magnitude. Viewed from the top, the X components of the fringing fields are actually in phase, leading to broadside radiation pattern, that is the peak radiation is in the Z direction. This model suggests an aperture field analysis approach where the patch has two radiating slot apertures with the electric fields in the plane of the patch. And for the half-wave patch case, the slots are equal in magnitude and phase, and the fields along the edges associated with the slots 1 and 2 are constant, whereas those along other edges seen in this side view have odd symmetry and their radiation cancels in the broadside direction and is usually neglected. A metal patch mounted at the ground level with the dielectric material in between constitute a microstrip or patch antenna. These are very low size antenna having low radiation. A microstrip antenna consists of a very thin metallic strip placed on a ground plane with the dielectric material in between. So the radiating element and field lines are placed by the process of photo etching on the dielectric material. Usually the patch or microstrip is chosen to be square, circular or rectangular in shape for the ease of analysis and fabrication. So this diagram shows the microstrip antenna image, and the length of the metal patch is lambda by 2. When the antenna is excited, the waves generated within the dielectric undergo reflections and the energy is radiated from the edges of the metal patch. The radiation pattern of the microstrip or patch antenna is broad. It has a lower radiation power and a narrow frequency bandwidth. The radiation pattern of a microstrip or patch antenna as shown in the following figure, let us see afterwards, and it has lesser directivity. To have a greater directivity, an array can be formed by using these patch antennas. And the main advantages of microstrip antennas are lightweight, low cost and ease of installation. And its disadvantages are inefficient radiation and narrow frequency bandwidth. Alright. And microstrip antennas can be used in spacecraft applications, aircraft applications and low profile antenna applications. Consider a microstrip antenna which is fed by a microstrip transmission line. The patch antenna, that is a microstrip transmission line and ground plane, are made of high conductivity material, typically copper, and the patches of length L and width W and sitting on the top of the substrate of thickness H with a permittivity of epsilon r. And the thickness of the ground plane or of the microstrip is not critically important, and typically the height H is much smaller than the wavelength of the operation. So this is the top view of the patch antenna, and which shows the ground plane and the microstrip transmission line and substrate. The frequency of operation of patch antenna is determined by the length. The center frequency will be approximately Fc is equal to C by 2L into square root of epsilon r. That can be written as 1 by 2L into square root of epsilon naught into epsilon r into mu naught. So the above equation says that the microstrip antenna should have a length equal to 1.5 of wavelength within the dielectric medium. The width of the microstrip antenna controls the input impedance, and large width can also increase the bandwidth. For a square patch antenna fed in the manner above, the input impedance will be in the order of 300 ohms. By increasing the width, the impedance can be reduced and the width further controls the radiation pattern. The normalized radiation pattern is approximately E theta is equal to sine of kW into sine theta sine phi by 2 divided by kW into sine theta sine phi by 2 into cos of KL by 2 into sine theta cos phi into cos phi. And E phi is equal to minus sine of kW sine theta sine phi by 2 divided by kW sine theta sine phi by 2 into cos of KL by 2 into sine theta cos phi into cos theta sine phi. So in this above equation, K is the free space wave number given by 2 pi by lambda, and the fields of the microstrip antenna is given, the radiation pattern is given in this figure. The directivity of the patch antenna is approximately 5.5 to 7 dB. Consider the side view of the patch antenna, and we can note that since the current at the end of the patch is 0, that is open circuit end, the current is maximum at the center of the half wave patch, and theoretically it is 0 at the beginning of the patch. That you can see in this figure. The current adds up in phase on the patch of the patch antenna as well, and however an equal current but with the opposite direction is on the ground plane, which cancels the radiation. And this also explains why the microstrip antenna radiates but the microstrip transmission line doesn't. The microstrip antenna's radiations arises from the fringing fields, which are due to the advantageous voltage distribution, and hence the radiation arises due to the voltage and not the current. The patch antenna is therefore a voltage radiator as opposed to the wire antennas, which radiate because of the currents add up in the phase and are therefore current radiators. So this diagram also shows the radiation pattern of a microstrip antenna. It is the fringing fields that are responsible for the radiation. And note that the fringing fields near the surface of the patch antennas are both in plus y direction. And hence the fringing fields and the edge of the microstrip antenna add up and in phase to produce the radiation of the microstrip antenna. Now let us see some of the feeding methods of microstrip antenna. And the first method is the insert method. Previously, the patch antenna was fed at the end. Since this typically yields a high input impedance, we would like to modify the feed. And since the current is low at the ends of the half-wave patch and increases in magnitude toward the center, the input impedance could be reduced if the patch was fed closer to the center. One method of doing this is by using an insert fed, and that is shown in this figure. Since the current has a sinusoidal distribution moving in a distance r from the n will increase the current by cos of pi into r by l. And the voltage also decreases in magnitude by the same amount that the current decreases, and hence using Z is equal to V by I, the input impedance scale can be written as Z of R is equal to cos squared of pi R by L into Z of 0. Right. And Z of 0 is input impedance if the patch was fed at the end. Hence, by feeding the patch antenna shown in this figure, the input impedance can be decreased. And the second method of feeding the microstrip antenna is fed with the quarter wavelength transmission line. The microstrip antenna can also be matched to a transmission line of characteristics impedance Z0 is by using a quarter wavelength transmission line characteristics Z1. So that you can see in this figure Z0 as the characteristics impedance of this is matched with the Z1. The goal is to match the input impedance to the transmission line. If the input impedance of the antenna is ZA and the input impedance viewed from the beginning of the quarter wavelength line becomes Z is equal to Z0, that is equal to Z1 squared by ZA. And this input impedance Zn can be altered by the selection of Z1, so that is Zn is equal to Z0, and the antenna is impedance matched. The parameter Z1 can be altered by changing the width of the quarter wavelength stripe, and the wider the strip is, the lower the characteristics impedance Z0 is for that section of the line. And the third method is the coaxial cable or probe feed. Microstrip antennas can also fed from underneath via a probe. The outer conductor of the coaxial cable is connected to the ground plane. The center conductor is extended up to the patch antenna. So that is shown in this figure. The position of the feed can be altered as before in the same way as the insert feed above and to control the input impedance. The coaxial feed introduces an inductance into the feed that may need to be taken into account if the hatch gets large. In addition, the probe will also radiate, which can lead to the radiation in undesirable directions. And then next method is coupled method or coupled feed. The feeds above can be altered such that they do not directly touch the antenna. For instance, the probe feed in this given figure can be trimmed such that it doesn't extend all the way up to the antenna. The insert feed can also be stopped just before the patch antenna. And the advantage of the coupled feed is that it adds an extra degree of freedom to the design. The gap introduces a capacitance into the feed that can cancel out the inductance added by the probe feed. Thank you.